back to second talk of Ankit. So he'll be talking about cohomology of arithmetic groups, the second talk of his. Okay, so he'll be talking about Matsushima formula and GK modules, etc. So Ankit, you can start.
Thanks, and I thank the organizers for this opportunity. Let me first list the references because I have not talked about the exact references of theorems, etc., that I mentioned. So this is like a famous book of Borel-Walla, continuous cohomology, discrete subgroups, and representation. Book of Bump contained many interesting, I mean, a lot of detailed proofs, etc., automatic forms and representation. And then there are these three notes. This is about automatic forms on GL2, which featured in last talk as well. And there's this talk by my advisor Arvind Nair called Title Matsushima formula. So these were prepared for 2000, some lectures in 2011, and these are notes by J.W. Hume. They were prepared for this Converse seminar in the group of Converse. So the goal is to understand what is meant by GK cohomology of a GK module, relate this to cohomology of locally symmetric spaces, and finally prove like a defined version of this relation in terms of Matsushima formula. Before we begin, let's see how GK modules arise. So the setup is, let G be a real semi-simple group. So we will mostly restrict ourselves to real points of an algebraic group defined over real. Fix a maximal compact subgroup K of G, theta beta Cartan involution associated to K. And so associated to this, we have this decomposition. Lie algebra of G is denoted by Gothic letters, and G decomposes K direct sub P into +1 and -1 eigenspace of the map induced by theta. UG denotes the universal enveloping algebra of G. So this is basically a universal solution to maps from G to any associatively algebra. So if you're not so familiar with it, it is simply the tensor algebra quotiented out by relations, the double-sided ideal generated by the relations of this form. So where this denotes the Lie bracket, bracket x comma y denotes the Lie bracket of G. So so this should be thought of as the remnant of the relation in like Lie derivative, which you have already seen, Lx Ly minus Ly Lx equals Lx comma y on manifolds. So of course over Rn x comma y becomes 0. So we of course are very familiar with the relation that partial derivatives commute for a smooth function, but okay. So if you have not seen this object, I thought to mention this. Zg will denote the center of the universal enveloping algebra. For SL2, it is something very familiar, and we will come to it later. Let's start with some basic definition. So before coming to GK modules, we will see what is first a G module. So a continuous G module, where G is a real semi-simple group. So a complex or real Hilbert space V equipped with this norm, and which is equipped with an action denoted by pi of G, is called a continuous G module if the map G cross V to V is a continuous map. So we will denote this by pi comma V. Sorry. A vector V in V is said to be smooth if the so it will soon become clear why we are looking at these notions. But first let's see a vector. Sorry, a vector V in V is said to be smooth if the orbit map from G to V given by G to G dot V, the orbit of V. This map is infinitely differentiable, and its derivative in the direction of x will be denoted by x dot V. Okay. So note that V is a Hilbert space. So one has to be slightly careful about what this notion precisely means. But nonetheless, instead of going into details, let me just leave it at that. So for convenience, x dot V is simply maybe can be just thought of as e power tx. So this is the one parameter group generated by x. Acting on V, and we differentiate with respect to that. Okay. So, so this is some subspace of V denoted by V infinity, which is all the vectors V in V such that V is a smooth vector. Okay. So an example: if S1 is acting on L2 S1 by right regular representation, just by pulling back functions, where S1 acts on the group S1 by right multiplication, and we pull back. And this gives a representation of S1 on L2 S1. So then L2 S1, the smooth vectors are precisely smooth functions. But in general, this equality is not true since S1 is compact, so something good happens. But of course, not all smooth functions are L2, so we should not expect this equality for more general representations. Okay. So this is a smooth vector. I mean, yeah. So I mean, of course, this look. So V infinity is a subspace of smooth vectors, and this is called yeah. Sorry, I don't know if there is a name, but okay, this is will call subspace of smooth vectors, and an element X in G. So it makes sense to talk about X dot V. In fact, for any X in UG, so it can be thought of as multiple, like all partial derivatives in all directions applied one after the other. So any element X in UG, it makes sense to talk about X dot V. So V infinity becomes a UG module. And that it becomes a UG module has to do with we are taking it smooth vectors. So the kind of identity that a derivative with respect to X, then Y, and Y then X, it sort of agrees with the derivative with respect to along the vector X comma Y, the Lie bracket of X comma. Okay. So you can also equip this subspace V infinity with another like family of semi-norms, and it becomes a fresher topological vector space with continuous G action. But we will not worry about this so much. Our aim is to go in a slightly different direction. Okay. So this is a result of guarding that the smooth vectors form a dense subspace in the subspace topology, not in this different topology. This topology does not, I mean, has some relation with the subspace topology, but it does not interact well. But in the subspace topology, this subspace is dense. Okay, so it says that looking at some nice set of vectors can tell us something interesting about the subspace, that it maybe in some sense determines it as well because it is dense.
What is omega? It's compact set.
Compact subsets of G. Yeah.
Okay.
Okay, so the next notion is of K finite vector. So a vector V in V is said to be K finite if the dimension of the span of KV for K in capital K is finite. Okay, so why are we looking at these things? So I mean, if we are in a slightly nice situation, then K finite vectors will be real analytic. So of course they will be smooth, so they will be contained inside V infinity. So the point here is to get cook up a very nice subspace where we can do a lot of interesting analysis and somehow get a lot of information about the continuous G module. But working with the continuous G module is maybe a little harder. So the point is to maybe get rid of topology and get to a more algebraic notion. Okay, so a space is representation is called admissible if K isotropic subspace of K finite vectors of V are all finite dimensional. Okay, so if V is admissible, then Vk is contained in V infinity. In fact, K finite vectors are real analytic. This is the result of Harishchandra, which I was trying to mention before. So first we started with some representation, which is like a huge Hilbert space. Then we came down to understanding only smooth vectors, which were dense in V. Now we have only K finite vectors, which is also dense in V. So, but this is more tangible. I mean, Vk as a representation of K can be understood much better because all the vectors are K finite. And if we in fact even more assume V is admissible, then as a representation of K, Vk can be okay, sorry, some notification. So Vk can be written as direct sum of isotropic subspaces for K, each of which are finite dimension. So it is much more understandable notion. Okay. This is something very familiar. So it is called irreducible if there does not exist a non-zero proper closed G invariant subspace. So we also demand closed here because of the topology that is there on V. And representation is called unitary. So if this is of course very familiar to us. If pi G are unitary bounded linear operatives. Okay, so then there is this result of Harishchandra which says that every irreducible unitary representation is admissible. So of course we have looked at a lot of notions. So just recall that admissible is something such that the K finite vectors, so the K isotropic subspaces of K finite vectors are all finite dimensional, right? So every irreducible unitary representation is admissible. And why did we introduce the notion of admissible? Because as we may see later, that admissibility is a better condition. Better condition in the sense that it is adapted for systematic study in terms of Langlands classification. So the notion of admissibility breaks down the problem of irreducible unitary representation in two parts. So first we can understand admissible, and then we can understand which of these representation is unitarizable. Okay. So this is all that we will talk about G module. So let's go to the notion of GK module, and we will see how do G module give rise to notion of GK module. So GK module is very algebraic in nature. That is there is no interaction with topology. So we start with a vector space. So for example, notice that there is no Hilbert space here. So a vector space we equip with an action of G and K such that such that V is semi-simple as a representation of K. This is the first condition. Second is, okay, so derived condition. First condition is then the K finite vectors equals V. That is, all vectors are K finite. So recall that K finite meant that span of K translates of vector V is finite dimension. Second condition is for any K in capital K, X in the Lie algebra, there is this condition hold. Of course, we would think that this condition should always hold, right? Because Kx, K inverse times K, that is exactly add Kx. So we will expect this condition. So this is called compatibility between the action of G and Lie algebra G and capital K. Maybe it is not, if suppose G were acting on V and we differentiate the action of G to get this GK module, right? GK module V, then it is not at all surprising that this should hold. But in general, we demand this condition. Okay. Next. If F is a K-stable finite dimensional subspace, then the action of K is differentiable. This is some general fact. Now, so we can differentiate it to get an action of this Lie algebra of capital K, which is given by Gothic K. And we demand that the restriction of the action of G on V restricted to the Lie subalgebra, Gothic K, actually agrees with the differential of the action of K. So this is another compatibility which you are demanding. That in fact, restricted to the connected component of K, sort of the action of G sort of determines the action on K. In fact, if K were connected, it is mentioned in, I think, Wogan's book that in the GK module, the K does not play too strong of a role if K were connected. This is also a corollary. I mean, this remark is a corollary of a result of Harishchandra, but I have not noted it down here. Okay, so there is again some similar notions as before. Pi comma V is called unitary if V is equipped with a positive different bilinear form such that this happens. So note that this is exactly what the relation we will obtain by differentiating the relation that we had earlier for unitarity. So this, you might be already have seen it before. It is called irreducible if there does not exist a proper non-zero UG invariant subspace. So we could have so note that there is no closed here. So we are like moving a little far away from topology and a bit more closer to algebra. A GK module pi comma V is called admissible if all K isotopic subspaces are finite dimension. So note that earlier we had that a representation is admissible if all K isotopic subspaces of K finite vectors are finite dimensional. But here, since all vectors were K finite, so we have this that we are reduced to considering the condition. We are reduced to considering only the condition that K isotopic subspaces are finite dimensional. Okay. So again, like we had previously, an irreducible unitary G module was admissible. So here we have some similar notion. An irreducible GK module pi comma V is admissible. So the so this is to convince you that the notion of admissibility is good. It contains some all irreducible modules. So we can, and in fact, it is better adapted for classifications of the represent GK modules as well in terms of like Langlands classification. I mean, that comes under the umbrella of Langlands classification. Okay. There's another very important notion which is called an infinitesimal character. So GK module is said to have an infinitesimal character chi pi. So we call that ZG what the center of the universal enveloping algebra. So UG acts on V. Hence, we can restrict the action to the center of the universal enveloping algebra, which is denoted by ZG. So we say that a GK module is have an infinitesimal character chi pi if there exists if the restriction of action of UG to ZG gives rise to this character. That is pi Z dot V equals chi pi Z dot V for all V in capital. Okay. Next, so there is a, okay, so we should mention here name Dixmuir. So we already know that Schur's lemma, that any the endomorphism of irreducible module is just scalars. So right. So we see that an element Z in capital ZG gives rise to an endomorphism of V to V, right? Because this lies in the center. So it commutes with the action of UG, right? So it gives rise to an endomorphism. So, but Schur's lemma, I mean, the classical Schur's lemma is only for finite dimensional representation, but Dixmuir has a Schur's lemma which holds for all GK modules of countable dimension. So an irreducible GK module is necessarily of countable dimension because for any vector V in V, we can take UGV and consider the submodule generated by UGV. This has to be equal to V because V was irreducible and UG has countable dimension. So V has countable dimension. So we can apply Dixmuir's version of Schur's lemma to get that an irreducible GK module has an infinitesimal character because any Z in ZG gives rise to an endomorphism, but this endomorphism have to be scalar, right? Whatever this endomorphism is, it has to be scalar. That scalar will be denoted by chi pi round bracket Z. Okay. So let's so we want to understand GK modules, but we earlier saw a lot about continuous G module and how are they related. So they are related in the following fashion. So let's see GK, we know the GK modules pi comma the category of GK modules, and a morphism of GK module will be a UG module, which will be a morphism as UG modules, which respects K action. So, okay, so how are these things related? So consider this continuous G modules, which we saw earlier, that is Hilbert space equipped with an action of G, such that G cross V2B is continuous. And we call this functor Harishchandra. I mean, we can name it to be Harishchandra functor. So I think that is what I have seen in many places, but I don't know if this name is very standard. So pi comma V is mapped to Vk, the k finite vectors of V, intersected with smooth vectors. So if V were admissible, then of course Vk is contained in V infinity, and this just becomes Vk. So call this to be HCV. So this is a GK module associated to V. This is how we can also write it. So note that of course V, right? I mean, so V infinity was a UG module. To make it to a GK module, we needed to ensure that whatever vectors we are considering, whatever smooth vectors we are considering, they are also K finite vectors. So we needed to intersect it with Vk to obtain this. So this is a GK module. Now, these are some results of Harishchandra, which I have summarized in this diagram, that irreducible, admissible, continuous G module maps to this Vk, right? Because as we have seen, this is a result of Harishchandra, that in an admissible continuous G module, Vk is contained in V infinity. So there is this map. This is surjective in the sense that given an irreducible GK module, there exists a irreducible continuous admissible G module, whose Harishchandra module is the GK module we started. Moreover, if you want to restrict to understand if you can further lift it to unitary admissible G module, then we don't know if it is surjective, but definitely it is injective. So that is every irreducible GK module. So there is exactly one unitary representation in that infinitesimal class. Okay, so this class associated to V mapping to this is called like it's infinitesimal classes. Okay, because infinitesimal, because we are looking at sort of like maybe in some sense derivatives around identity of the group G. Okay, so let's look at some properties of GK module. So the GK modules admit subquotients. Okay, maybe this is not so hard to believe. It admits duals, but we have to be slightly careful. So the contra gradient, so given a UG module, we can define this contra gradient representation of UG on all linear functionals on the space V. But we have to be slightly careful because this entire space may not be K finite. So we only have to take K finite vectors of V dual and we denote it by V tilde. So it admits dual. So note that this is forced on us because by our definition, GK module are things which only consist of K finite vectors. Okay. So, but there is something, but we expect that V double dual or V double tilde should equal V. In fact, it is true if V were an admissible GK module. So the notion of admissibility is also, featuring here in the sense that it is a nice notion. The expected things hold. The category admits enough projectives. So let me not go into the construction, but rather just say that, okay, so this admits enough injectives and the trivial GK module, in fact, admits the following projective resolution. So why are we looking at this enough projective condition? Because this allows us to compute cohomology, right? Because whenever we want to compute cohomology, for example, in the classical setup for R modules, we needed to know that every R module can be resolved by projectives. So here also, we need to know that every GK module can be resolved by projectives. In particular, if we want to compute cohomology of U in the category of GK module, or rather compute X functors of C comma U, which as we know, generally referred to as cohomology of U, then this X functor can be computed if C would admit a projective resolution. And the claim is, which is there, this explicit construction is there in Burel-Wallach's book. I shall share the notes later and have like precise reference for this. That this, in fact, some definition is there, right? So consider CQ to be UG tensored with wedge Q with extra power of G mod K. So this is a K module. So it will become this will become a UK module, and UG is of course the right UK module. It is also a left UG module. So this is the structure of UG module on this, rather G module, and then K is the structure of the action of K is by tensor product of adjoint representations on both. Okay, that everything makes sense, needs checking, and these are the differentials. So let me not go in here, but the point is we can use this to compute X functors in this category. Okay. So an irreducible GK module admits infinitesimal character. We have already seen this. In fact, something more general is true. Every finitely generated UG module says that it is also this ZG finite, says that every vector in V is ZG finite. This is then also V is admissible. So the above this corollary of Dixmuir's version of Schur's lemma can also be strengthened, and this is also a corollary of some result of Harishan. Okay, so let's come to an interesting corollary that if UV are two GK module with infinitesimal character chi U and chi V such that they are not equal to each other, then there cannot be any extensions between of U and V. That is, all X functors from I bigger than or equal to 0, they all vanish. Okay, so how to check this? The main point is somehow again use that Z in this center of the universal unwrapping algebra acts on both U and V. So it gives an endomorphism of this module, this vector space, right? Because Z acts on V. So it will, if you believe that X I U comma V is a functor in both the variables, so we should get two endomorphisms of this vector space given by Z, one by multiplication on V, one by multiplication on U. But note that when multiplying by Z on V, it is by the scalar chi V of Z. When multiplying Z on U, the induced map of the vector spaces, vector space Xi, will be multiplication by chi U of Z. But suppose you can prove that the two multiplication, that the endomorphism induced by multiplying z on v or u agree, then we get that chi v z must equal chi v z, chi u z must equals chi v z. But we know that there exists a z where they are unequal, right? Because we begin with the assumption that chi u not equal to chi v. Hence, the x function have to vanish. Okay, so maybe the proof was a little quick, but nonetheless, maybe I should go ahead and let it rest for time. Okay, so this is a nice. Okay, so this sort of justifies why we can, why the looking at GK modules is interesting. So let pi comma v be an additional representation of G. So closed G invariant subspaces of V. I mean, there is a map. I mean, we can apply HC functor that we saw before to get sub GK modules of the associated Harishchandra representation of this Harishchandra GK module to V. And there is a 1-1 correspondence between them. What it says is, in particular, that irreducibility can be checked algebraically. That is, if we want to check if V is irreducible, we can look at only the Harishchandra associated Harishchandra module and check if the associated GK module denoted by HCB is irreducible, right? And let me just maybe mention the corollary itself. Two irreducible unitary G modules are equivalent, okay, if and only if. So this it is missing here. It should read two irreducible unitary G modules are equivalent if and only if their associated Harishchandra modules are equivalent as GK modules. So that is irreducibility, and whether they are isomorphic, they can be checked after going to the associated GK models. So it sort of justifies why we can, but of course the GK modules is more maybe in some sense easier to handle because they are more algebraic in nature. Whereas the continuous G modules, it had some flavor of topology and some flavor of analysis. Okay, so let's look at some examples. So this is very familiar to us. We have this group S1, which is a compact group. We can look at a measure. We have a biinvariant Haar measure on G, such that the volume of G is equal to 1. So consider right regular representation of G on L2G. So we have already, you might already be familiar these kind of representation from like this Peter Weil formalism, right? I mean, there's some theorem which understands what is L2K for K compact. Okay, so but this is much more elementary than that. So let's G hat denote homomorphism from S1 to C star, which we know is Z. Then L2G decomposes as C chi, where chi's are all the characters. Okay, so this is a Hilbert direct sum. That means we take the direct sum and then complete it under the L2 norm. So we can look at the subspace of direct sum over these functions C chi, where chi is a character, and then complete it under the L2 norm. And this is an equality. Right, so we are able to decompose L2G in terms of translation invariant, or rather eigenvectors with respect to translations on S1, right? Because if we act by S1 on chi, it will transform as the character chi, which we can take like Z goes to Z power n. So if chi is Z goes to Z power n, then it will translate like that. So we have managed to decompose L2G as some of eigenvectors. But note that situation is not as simple in general. So for example, L2R, if you look at the right regular representation of the group on L2R, then although it has countable orthonormal basis, but not one where which can be given by eigenvectors, which can be given by elements which are eigenvector with respect to translations, because functions of this form are not in L2. But L2 does have many sub-representation, L2R, but it does not have any irreducible unitary sub-representation. So these are some some difficult examples which do arise. So we do have to deal with it, but I will not be talking more about it here. Okay. So here we have a okay. So when talking about GK modules, we have this nice proposition where if you look at the group G is equal to SL2R. So here we are working with SL2C actually. But it's not. I mean, the point is, this proposition sort of lets you understand what is a GK module when we are working with the group SL2R or GL2R plus, something which we have already seen in the last lecture. What is it? So it lets us understand classification of irreducible admissible GK modules, which are very simple, and it can be understood in terms of three vectors H, R, V. So H sort of generates K, the compact subgroup, or rather the complexification of K. R and L are whatever are called as raising and lowering operators. So let's see why such a name. So let V be an irreducible GK module. Then V restricted to K by our construction, by these assumptions, will decompose in terms of isotypic subspaces. But K is just S1. So it decomposes as these characters where L denotes the character Z goes to Z power L of S1. Right. So then we have these small, computations which can be done to deduce all this. That VL equal to eigenvectors of H with eigenvalue K. If V in VL, so that is why R is called a raising operator, because RV belongs to VL plus 2, LV belongs to V of L minus 2. And yeah, so if V is non-zero, then in fact RV and LV generate the subspaces VL plus 2 and VL minus 2, and in general for any higher iterations of these. Okay, so these are some properties which we have. But okay, what I wanted to point out is somehow the representation is more or less determined by these things, in the sense that let's come to this interesting operator omega in ZG. In fact, when we are working with SL2, then center of the universal enveloping algebra is exactly generated by the Casimir operator. So omega, what we defined above, is the Casimir operator. So it says that somehow understanding the action of omega, or rather the infinitesimal character of V, and a little more data about this raising and lowering operator determines the infinitesimal, the irreducible admissible GK module V. Okay, so let's skip 4 and come directly to 5, which is sort of converse of 4, but maybe you can ignore it for a moment. So suppose the Casimir operator acts by this element. We have already seen that if V were an irreducible admissible GK module, then omega will act by a scalar. Suppose it acts by this scalar, L minus 1 square minus 1, where L is an integer. So of course, it is not necessary. It can act by some real number, but of course, always a real number because it is self-adjoint. But suppose it acts like this, and suppose VL is non-zero. Okay. And suppose VL is non-zero, then we can prove that L, the lowering operator applied to VL. So recall that VL was the L eigenspace of K and the action of K. So L applied to VL, that is a lowering operator applied to VL, is 0. So that is, the entire module is generated by R by choosing a vector V in VL and applying RV, R square V, R cube V, and so on, and considering a subspace generated by this direct sum. Similarly, if V minus L is non-zero, then applying raising operator on this gives 0. That is, the entire GK module V is given by this direct sum CL, by just applying lowering vectors where V is in V minus L, and similarly for the other thing. And if both VL and V minus L were 0, then V has to be a finite dimensional irreducible module isomorphic to this L minus 2 with symmetric power of the standard 2-dimensional representation of SL2R. So this is kind of a key classification theorem, and unfortunately we cannot go into the proof of this, but let's see an interesting corollary of this. Okay, so we continue the example. So let G equal to GL2R plus H is upper half plane. So this is something we discussed last time. Consider the space of functions, holomorphic functions from H to C, such that they are L2 under this norm. Note that this is slightly modified norm. Um, it is possible to check that this is the Hilbert space. And suppose we are giving the action of GL2R plus on this HK as follows. Okay, so these recall that these are automorphic factors, power minus k. Okay, so then it is possible to check that this is a unitary representation with orthonormal bases being this. Okay, so this is some computation. But the point is, these are exactly k plus 2n eigenvectors for the action of k theta. So we recall that k theta was the matrix uh, cos theta, sin theta minus sin theta, cos theta. Okay. Recall that to such functions, I mean, this is of course right. Uh, um, yeah. So I mean, this is a function on SL2R quotient SO2. So there was a way to translate it to a function on SL2R, but which was by multiplying it by certain automorphic factor. Right? I mean, we saw this sort of a dictionary last time, how to translate modular form into automorphic form. So it is part of that package. So let Pn be such that Pn of G is defined to be this. Then it is possible to check that Pn in fact belongs to L2G. Pn of Gk theta equals e power I k plus 2n theta. So here, earlier the representation was left. Sorry, the action of the group was from the left because we used inverse here. Here, the action of the group is again on the right. So something to be a little careful about because it can change this dk plus 2 minus. Anyway, nonetheless, so phi n of gk theta satisfies this and L phi n equals 0. So recall that L phi n equals 0 was just saying that it comes from a function which is holomorphic. Okay, so as a corollary of all this computation is that pi comma h is isomorphic to direct sum C phi n hat, and this is whatever is called as holomorphic discrete series. Okay. Right. So what I wanted to say here is that so note that it is also possible to check that. Sorry. Yeah. Right. So this is right. So exactly this is what we wanted to say that the lowering operator applied to this. There is something wrong. Right. Okay. Fine. Yeah. So right. So we can show that this Hilbert space representation is whatever is called as this holomorphic discrete series denoted by dk plus. Moreover, in the above whatever dictionary we were seeing, and okay, so I could not repeat the computation from last time. This cusp forms can be described as all the L2 functions such that these conditions were satisfied. Phi of gk theta is e power ik theta phi g. L applied to phi was 0 and omega phi equals this. But from the classification before, we have seen that this is exactly these conditions that omega acts by k times k minus 2. The lowering operator kills the vector, like a given vector, and that it translates by eigenspace k, exactly determines the this module which we have denoted by dk plus here. And okay, so the point is that this can be understood as f v, where f is a homomorphism from dk plus to L2 cusp. Okay. And where we should think of this as, sorry, the smooth vectors here. Yeah, sorry, I think this was not maybe not present in the optimal way, but nonetheless, let me go ahead. Note that dk plus whatever we saw above this Hilbert space This also appeared in the last talk, and it was all the functions which were sections of omega tensor K, where omega was the cotangent bundle of upper half plane. Okay, so let's come back to GK cohomology. So this is an explicit complex, which, as we alluded to before, that we could compute GK cohomology of a module by looking at some projective resolution of trivial representation, and it is exactly that. So we use the projective resolution of trivial representation, apply Hom dash comma V to get a complex, and that complex is exactly what is being written here. Right? So we begin with a GK module. We define this cochain complex where CQ is K linear maps, where the action of K on this module is via adjoint representation, and the action of K on V as given. So we look at this vector space, and we define the differentials to be the following. So it is something maybe it takes some getting used to, and of course, it is motivated by whatever we have seen in the Ram cohomology theory. Okay, so we have this chain complex with some vector spaces and some differentials. So this is, of course, it needs verification that dq composed dq plus 1 equals 0. But granting that, we can define the GK cohomology groups of pi comma v to be the following. So just the kth cohomology of this complex. So observe that the GK cochain complex is obtained by applying Hom dash comma V to projective resolution of C. We have already said that before. And okay, so this is some general theorem. So note that by construction, so let me just go back. So by construction, whatever is the dimension of G mod K, if we take Q to be bigger than dimension of G mod K, then this is 0. Hence, CQ is 0. That is, the cohomology automatically vanishes for all Q strictly bigger than dimension of G mod K. So there is this corollary that if UV are to some nice, like finitely generated admissible GK module, in particular any irreducible unitary GK module or irreducible admissible GK module, then X functors vanish after Q bigger than dimension G mod K, and by definition they vanish for Q strictly less than 0. Moreover, this admissibility requires allows us to say that they are finite dimension. So these are certain nice things which we know about. Yes. Okay, so now let me come back to this. Let me start by saying what is Matsushima formula. So the setup is as before. G is a real semi-simple group, gamma is a discrete subgroup, and A is a finite dimension irreducible representation of gamma. Let omega I denote G. I forms valued in the representation E. Okay, so we can define action of this group gamma on this I-valued forms as follows. In fact, an action of the group G, but here it is only the action of gamma which concerns us. So small gamma applied to omega evaluated at H, right? So this gives a linear functional, not evaluated at H, but looking at this as a linear functional on exterior power of THG. It can be evaluated at an element of this vector space, and we define the action to be as follows. Right? Okay. So now note that the G is of course a group, so we can trivialize the tangent bundle of G. So using this, we can define an isomorphism between I forms valued in E to homomorphism, just vector space homomorphism from exterior power of G to C infinity G comma I in the following manner. So omega is associated to a function phi omega evaluated on a vector here X. So this is a function which evaluated on G is simply this. Okay, so it needs some checking, but we can verify that this is in fact gamma invariant, where the action of gamma is on C infinity G comma E by left multiplication. Okay. Sorry. No. The action of gamma on C infinity G comma E is as we have described above. So we have described the action on I forms. We take I to be 0. You get action on all smooth functions. And that is the action of gamma on C infinity G comma. I'm sorry for the confusion. So we can check that under this action, this is a gamma invariant isomorphism. So we can take, we can look at what happens at gamma invariant sections, right? So it gives us an isomorphism between gamma invariant sections here, and then the action of gamma is only on the module, is only on this right hand side. So we have this, right? But this can be understood as smooth sections of certain flat vector bundle E tilde on gamma, on G mod gamma, where this is the standard associated construction, right? So we have a representation of gamma. We can cook up a local system or a locally a flat vector bundle on G mod gamma by this standard construction that we do. Right. So, we can look at gamma invariant sections of this as just smooth sections of the associated vector bundle on the quotient space. And similarly, this equality of the left and the right hand side can be extended to all I forms. That is, we basically get that omega I, G mod gamma, the I forms valued on E, and this vector bundle or the local system E tilde is same as homomorphisms from I the exterior power of G to C infinity G mod gamma E tilde. Okay, so we have these two equality, but what we want to understand is I forms on G mod K mod gamma, right? So let's see what that is. So we can similarly associate a vector bundle, or rather flat vector bundle on this associated to the representation E of phi 1 of this space, right? Because G mod K is contracted. Okay, by the same construction that we saw above. So the I forms valued in E over G mod K mod gamma is actually can be thought of. I mean, we can pull back this I form to an I form valued in E tilde over G mod gamma, right? So there's a quotient map from G mod gamma to G mod K mod gamma. We can pull back forms, but now we want to, but we understand this space very well. That is, we understand this space in terms of this as this mod, this nice vector space. So we want to understand what are all the forms which pull back to forms here. That is, we want to understand what forms are coming as pullback of forms here. So those are exactly, so let me not go into this, but allow me to skip ahead and say that those are exactly functions which sort of factor through K, that is, they factor through wedge I G mod K. So this is should be understood as interior product with any element X in the Lie algebra of capital K with omega should vanish. And the second is that F is K invariant, where the action of K is on the right, yeah, on the right on G mod gamma. Okay, so but if we incorporate these two conditions, this is exactly this space, right? Now, if E were obtained as a, suppose E were actually a representation of the group G, then E tilde can be trivialized and we obtain in this isomorphism of representations of G, where G acts here by right translation on G mod gamma, and here as tensor product of actions of G. So G acts on E and G acts on this space by right translations. Right, so E can be trivialized to obtain this isomorphism. So finally, we get that omega I G mod K mod gamma, this I forms valued in the flat vector bundle E equals hom K wedge I P, where recall that P was the K plus P of the Cartan decomposition and valued in, so we are looking at, yeah, this K homomorphisms in C infinity G mod gamma E tilde, but then this is isomorphic to this. So finally, we get this isomorphism. Right. But note that this is exactly the ith element of the quotient for the GK, for the quotient complex which was used to compute the GK cohomology. In fact, it can be checked that the above is an isomorphism of complexes. That is, so let us state this in terms of proposition. So let G be a real semisimple group, gamma a discrete subgroup, E a representation of G. Let script T denote the local system associated to the trivial local system on G mod K. Then we have this isomorphism of complexes. And this induces an isomorphism at the level of cohomology. Okay, so until now, representation theory has not come in, but now we have translated the problem of understanding cohomology of G mod K mod gamma in terms of understanding the GK module C infinity G mod gamma tensor E. So now what is this GK module? So here we assume that gamma is a discrete subgroup, discrete cocompact subgroup. Right, so cocompact means that G mod gamma is compact. So this will imply that G is unimodular, hence there exists a biinvariant Haar measure on G, and we can take the quotient measure on G mod gamma. Since G mod gamma has is compact, this has finite volume. We can normalize the measure to have volume 1. Denote this measure by mu. Consider the L2 functions on G, where we equip it with the norm norm f. Square is defined to be mod f square d mu, integral with respect to this representation. Okay, so then this is, as before we have seen, G acts on the space G mod gamma on the right. So this is a right regular representation. And because of the normalization of measures, etc., this is moreover unitary. So we have a unitary nice representation of G. Now, since G mod gamma is compact, so here we are using G mod gamma being compact crucially, we have this equality, right? Because in general, smooth functions may not be L2. So here we get that, just like for a group like S1, we got that smooth functions were actually smooth vectors in the right tabular representation L2 G mod gamma. This is crucial for us. This gives us the way to understand this GK module as the Harishchandra module associated to a unitary representation. But we understand the structure of this representation well due to this famous theorem of Gelfand-Pietraszky-Shapiro, which says that L2 G mod gamma as a right regular representation of G as a unitary right regular representation decomposes into countable Hilbert direct sum. So this set is countable. The representation which appear here is countable. We can take the direct sum and complete it under the L2 topology. M gamma comma pi. These are the multiplicities with which a representation pi appears. This is finite, and pi is unitary and irreducible. In particular, it is admissible. So we have this theorem of Gelfand-Pietraszky-Shapiro, which tells us a lot about the structure of L2 G mod gamma. So in light of this, we earlier had that H star G mod K mod gamma with values in this local system E was isomorphic to GK cohomology of C infinity G mod gamma, but C infinity G mod gamma is smooth vectors of L2 G mod gamma. So we can translate like this, right? Now we want to say that since the left-hand side is finite dimensional, hence there can exist at most a finite subset S prime of S, that is finite subset. So this set S is also sometimes, I mean, it is a subset of G hat, which is all the unitary representations. Okay. So there exists a finite subset S prime of S such that H star GK pi infinite tensor E is 0 for all pi outside S prime, right? Because whatever is the dimension, there can be at most that many irreducible representation with non-zero cohomology, right? Because we can split it off. So for any finite subset S prime, we can split off this GK cohomology of this module as these two direct sum. So it says that there can at most be only finitely many pi infinity such that this space is non-zero and M gamma pi is non-zero. So there are only finitely many such things. Okay, this is the first thing. So S prime is some finite set, direct sum, something, whatever remains. But the key point is for all pi in S minus S prime, H GK cohomology of pi infinity tensor E is 0. But here we are looking at infinite, a countable Hilbert direct sum and smooth vectors of this. So it is not clear and probably even not true that this equals direct sum of pi infinity. But here we need a technical lemma from Borel-Wallach. This book, this lemma is listed here, that this is in fact zero. So if each of the representations appearing in here, if individually the cohomologies are zero, then the cohomology of the countable Hilbert direct sum is also zero. That is, we get that this entire term vanishes. So we are left with only this term. Right. So let's just go back. So this is what we are interested in. It is GK cohomology of L2 G mod gamma smooth vectors, which is just direct sum M gamma pi F star GK pi infinity tensor E, such that these are non-zero and M gamma pi is also non-zero. Right. So this is, maybe we can skip this for now. So I mean, we can right. Okay. So this remark is actually maybe more pertinent. So note that S prime is all the representation pi in S such that the infinitesimal character of pi. So recall that pi was unitary admissible. Sorry, unitary irreducible. So hence this is an infinitesimal character. So we require that chi pi equals chi e dual, right? Because if we want this cohomology to be non-zero, this can be seen as x of e dual comma pi infinity. But then infinitesimal character of E dual should agree with infinitesimal character of pi. Okay, so S prime is a subset of this. The latter can be shown to be a finite set. So all unitary representation such that chi pi equals chi E dual, that is the set of unitary irreducible admissible set of all unitary irreducible representations of G whose infinitesimal character is given to us is a finite set. But this is non-trivial theorem. It depends on some sub-representation theorem, some results of Harishchandra and some Castleman, results of Castleman. And I believe it will be discussed in the next lecture, perhaps. Okay, so we get that this also allows us to show. So if we can, by some other method, show that this is a finite set, then we can repeat the entire argument without needing the fact that this was finite dimensional. So what we're able to show here is that if we can show that this is a finite set, then we can get the finiteness of cohomology as corollary. But we have seen such results before as well, like finiteness of dimension of space of modular form was a corollary of some difficult result of Harishchandra on finiteness of space of automorphic forms with certain certain constraints. Okay. Note that one can understand what is Laplacian on I forms in terms of infinitesimal character, and this allows us to recover Hodge theory on G mod K mod gamma. So this is a part of the package of Matsushima formula, but this is covered in the chapter 2 of Borel-Wallach, but we are completely skipping it. Okay, so this is like finally the theorem of so maybe this can be thought of as Matsushima formula. Let me just read it out. Okay, so I don't know. Sorry, this doesn't make sense. Let G be a semi-simple, real semi-simple group. Yeah. Gamma be a co-compact discrete subgroup now, which acts freely on G mod K. So we can assume this to get that G mod K mod gamma is a manifold. Otherwise, it can have some finite intersection with K. And anyway, safer to just, and that can always be achieved by taking gamma to be small enough. Let E be a finite dimensional representation. So we take it to be reducible, but maybe this is not a very serious constraint. Representation of G, then we have this following isomorphism. That is, the ith cohomology of G mod K mod gamma with respect to local system E is isomorphic to M gamma comma pi, which was the multiplicity of pi appearing in L2 G mod gamma times, so this is the multiplicity of this vector space, and the vector space is given by Hom K, which I P, comma pi infinite tensor. So note that it says that so wedge IP for I vary and this P is fixed. So it says that there are some K types which must appear in pi infinity tensor E. So this would be seen to be one of the important ingredients to ensure that a representation is cohomological. So this will also show later. Okay, so let me just end with this example of discrete series, which you've already seen. So recall that V is equal to dk plus. So dk plus was So maybe I'll just write it here. So this is equal to direct sum L, where L is bigger than or equal to K, and omega, the Casimir operator, acts by the scalar K times K minus 2. So there could be some different, with respect to different normalizations, we can give different number here. So maybe with respect to the normalization that I am following, it is K times K minus 2. So recall that this was the GK module, irreducible GK module that we have. Applying L to the kth subspace here is 0, and applying R to dk plus round bracket K, which is the kth isotopic component of SO2, the maximal compact subgroup in SL2R. Yeah, so applying R multiple times, we can generate this entire subspace. So I'm just trying to recall what was dk plus for you. This is called as holomorphic discrete series. Okay, so so this is some competition. So suppose we want to compute the ith cohomology, the GK cohomology of dk plus tensored with nth with some local system. So we can safely assume it to be, I mean, since we know that all the finite dimensional irreducible representation of SL2R are of this form, Lth symmetric power of standard two-dimensional representation. So this is non-zero. Well, first of all, implied that the infinitesimal character at omega equals are agree, right? We have seen this. This can only hold if and only if this is some computation. So this we know that chi dk, whether at omega, is k times k minus 2, and this is L times L plus 2. So this is some computation which you are skipping. This can only happen if L is equal to k minus 2. So when L is equal to k minus 2, then this equals Hom k. This is what we have seen before. P, the in the k plus p. This is the G mod k, comma dk plus tensor this. Right. But note that yeah. So P complexified splits up into, so instead of looking at with real representation, we can in fact tensor it with C for the ease of computation. So, right, I mean, so we can tensor everywhere with C. So P complexified splits up into P plus and P minus, where these are +2 and -2 eigenspace for the action of K, adjoint action of K on this, right? So, so that is, there are only, but we want this to intertwine with this representation. But looking at the k isotopic components in all this, and like a small computation using this this description of dk plus, we get that so we get that it equals 0 if I is not equal to 1, and it equals c if I is equal to 1. But note that 1 is exactly equal to dimension of G mod k by 2, which is the middle degree. Right. So right, so that yeah, so the fact that H1 is non-zero is sort of reminiscent of the fact that there exists such a short exact sequence of GK modules, that there is an extension of sim k minus 2 standard two-dimensional representation of symmetric k minus 2 symmetric tensor power with dk plus some dk minus. I think for k odd, otherwise we need to put some signs here appropriately. So I think I'll end here. There is an adelic version of Matsushima formula, but I don't have time to discuss. Thank you for your attention. If there are any questions, you can let me know. But whatever I've said is contained in the notes I have said here. I have borrowed heavily from especially the notes that I have mentioned in the beginning, which I'll go to the first page for your convenience. Thank you. Thanks.
Ankit. So
Yeah.
when you said that in GK module definition, if K is connected, really K doesn't play. What do you mean by that?
Sorry, K is connected.
K doesn't play much role.
Yeah, so this is some remark in the book of Vaughan, which was, I think, representation of real reductive groups. So he stated a theorem of Harishchandra to justify his remark. But maybe I can send you the citation later.
Right,
I have forgotten, yeah, the result now.
Thank you.
Yeah.
What was the statement though? Oh, yeah. Okay. You don't remember the statement?
No, sorry.
Okay. No problem. No problem. Fine.
No, I think one can understand this, maybe the K invariant in of the ring UG well, and somehow this was playing a role is maybe, sorry, maybe I'm saying something even more wrong.
Okay.
Um,
there-
maybe
Okay.
I can look up the citation.
Are there any other questions? So if not, let's thank the speaker and okay.
Thanks, Ankit, for the nice talks.
Yeah, thanks. And yeah, it was, I learned a lot while preparing.
You can send us the slides later, maybe.
Oh, yes. I will maybe